But let's start with a couple of words about myself. I've recently co-founded a company called Muves. This is a company working on multilingual and multimodal search. As my day job, I'm a senior product manager at TomTom in search unit, focusing on relevancy and machine learning. I've been also a contributor to the tool Cupid. Alessandro mentioned the topic of analyzing the quality of search, and Cupid is another tool that you can use in this regard. I've been dabbling in search for 16 plus years, working in different startups and also working on web scale search. And you may or may not know me as a host of the Vector podcast. And this presentation is sort of like a short report of the first season of the Vector podcast. I'm also blogging on Medium, so if you're interested in vector search and getting practical, you can subscribe to my Medium blog. All right, so as I said, this will be a quick report of the first season of the Vector podcast. I will then go into vector search algorithms. Of course, I will not be able to cover everything, but I will cover some of these that I believe are quite important and good to know. I'm going to show you my vector search pyramid that I kind of invented probably like 7 months ago. And I keep revising it as I give new presentations because new players come up and they have interconnections and so on. I will also give you my version of use cases, and this is where I value your input. So please come up, or maybe you can share a use case that is dear to your heart. And I will conclude with where things are going, in my opinion. And of course, I will also show you the promised demos. All right, so what's Vector Podcast? Excuse me. It was launched October 13 last year. And by now it has 11 interviews. So it's like one-on-one deep discussions with the makers of vector search systems, databases, algorithms, embedding layers, and so on and so forth. It also has 2 lectures. So to some extent, Vector Podcast aims to be educational, and also interviews have very vast, show notes, and so you can kind of spend some time educating yourself following these links. It also has 2 webinars that I happen to co-host or host rather at CoRise. It's one of the educational platforms that appeared quite recently. We also did 1 live recording with 4 guests, and Alessandro Vendetti was one of the guests at Berlin Buzzwords. So please take a look. It's the latest episode. I didn't put it here. It also has 1 designer, Zaurab Rai, who has been super generous to help me design Vector Podcast. I'm not a designer. I'm a maker and technologist, but he's an amazing designer. All right. So the topics that are covered in the podcast are on this slide. These are just a couple screenshots of few episodes in no particular order. So the topics are like this: vector databases, and I spoke to the makers of VV8, Quadrant, Milvus, Vespa, Apache Solar. We have some of the makers and developers of these systems here on this Zoom call. I also spoke to the makers of neural search, and the examples are Gina and ZeroAI. Gina is open source, ZeroAI is closed source, but both of them are fairly interesting systems. Also, I drilled down into the algorithms, and I spoke to the creator of the most famous HNSW algorithm, Yuri Malkov. You can see his, this is the screenshot of the presentation of the talk. And I also spoke or presented about other approaches like doc2query and Bi-Encoders, and I will cover some of them today. I also spoke to embedding layer creators. At this point, I know only of 1, it's Mighty, but there are others that I could probably speak to. And if you feel like some of the topics are not covered or some of the players are not covered, let me know which. And I also did cover sparse search. So sparse search, which is keyword search, has been dominating the search market for quite a while, including machine learning, like learning to rank. So you will find a couple episodes on these topics. So all this says, please subscribe, there will be more. Okay, so I first wanted to give a very quick intro into how vector search compares to keyword search. So in keyword search space, you know, the famous examples are Elasticsearch, OpenSearch, Solr, Lucene itself, and it relies on matching of search terms, right? So essentially you build this fairly old data structure, inverted index, where you can probably find it at the back of each book or almost all books, where you have a word and a page number, except that in inverted index, you will have a word and a document ID. But it kind of makes it kind of difficult to find items with similar meaning, except for the cases when you can create your own semantic dictionary, and then you can control the way the words will be associated with each other, or maybe phrases. But again, this will require some uplifting, right? And it's also not directly suitable for multimodal or multilingual search. Okay, multilingual you can still achieve with some additional work. Multimodal, no, you cannot index images in a inverted index. At least I don't know of such examples. And this is just a sample query, a bear eating a fish by a river. So the result of an untuned keyword search in OpenSearch will find heron eating a fish. So you can see that it did focus on the action and the object, but it kind of forgot that the subject of this query was a bear. Conversely, in vector search, we deal with neural networks, and they represent objects like text, image, song, something else, and queries in high dimensional space. And so ranking is going to be based on vector similarities, similar to what we've learned in high school, I guess, in algebra classes. And it allows by design finding similar items with similar meaning of different modalities. So I can actually search with text, I can find images. Okay, so the same example, a bear eating a fish by a river, is going to be represented as a vector. In this case, I used clip model, so it will have 512 dimensions. And essentially the results will also be vectors, because that's how we find them. And the associated image is a bear eating fish in the river. So it's fairly relevant. Okay, now that promised vector search pyramid. So we're going to be focusing on the base of this pyramid for now, but you can see that in the base, we start with the algorithms. So these algorithms have been designed and implemented many years ago. Some of them probably like 10 years or more ago, some of them more recent. And they have two groups, KNN and ANN. KNN is exact nearest neighbor search. So in a nutshell, it's trying to basically to be exhaustive. So it will search all of the vectors available in your database to find the nearest neighbors to your query vector. At scale, this doesn't necessarily work, because if you have billion vectors, if you have 1,000 vectors, it may work. But if you have billion vectors or even 10 million, you know, the complexity is quite high. And so in this case, we resort to approximate nearest neighbor algorithms. And the examples are HNSW, which I mentioned before. We also have product quantization, inverted file, locality sensitive hashing, Zoom, DiskNN, BuddyPQ is an algorithm that we embedded in my group. And the existence of these algorithms has breeded the creation of vector databases. Of course, it was not the only reason why vector databases exist, but in many ways, thanks to these algorithms, we do have vector databases like Muves, V8, Pinecone, and so on. And also, if you look at how it's implemented in Solr or Elasticsearch, it's HNSW algorithm. And then if we go sort of one layer up in understanding what is it that we're building, neural frameworks, like Haystack from DeepSet, Gina from Gina AI, or Zero AI, Hebia, Feature Form, are all examples of this kind of meta layer that allows you to now build end-to-end backend systems that will essentially implement your neural search scenarios. And what's interesting is that between these two layers, neural frameworks and vector databases, there is a link. For example, Gina offers a Docker array data structure or abstraction, which allows you to implement support for, Pinecone or VB8 or Quadrant. And so now you can actually connect and use database as your storage and neural framework as your layer for conducting the neural search operations, right? Then you move one level up. So we're getting closer to the user here. You concern yourself with selecting an encoder, and this will depend on what use case you're solving for, and what kind of data you have, and so on. And what's interesting is, yes, you can select transformers, you can select GPT-3 model if you want, or go with BERT. But it's quickly going to be a bottleneck at scale to compute the embeddings, especially of high dimensions. And there, Mighty is something that recently came on the market, developed by Max Irvin, which allows you to move the cost of computation from GPU to CPU. And I know that Mighty is implementing support for various databases like Quadrant, and I believe VB8 was in the progress. Then you move one level up again, and now when you have all these, let's say, so-called moving or non-moving blocks, you need to think about your application business logic. And of course, if you have already an existing search engine like Apache Solr or Elasticsearch or OpenSearch, you might be using sparse search feature ranking like BM25. But then you want to also introduce this semantic layer, semantic richness into your in the mix. And what you will need to do is figure out how do you combine the results of these two approaches, because in many ways they will be sort of like competing. Neural might be optimizing slightly more for recall, but also for some semantic features. BM25 might be optimizing for some other use cases. For example, exact phrase search might be only supported by BM25 and so on. And then of course you need to build user interface and make your user happy. Okay, so we're going to be focusing on this base of the pyramid. And just to give you a broad overview, there are, quite a lot of players in this market, right? So big players like Microsoft, Spotify, Amazon, Google, Yahoo, Facebook, Baidu, Yandex, all of these, NVIDIA and Intel, they all have one or two ANN or KNN algorithm. Facebook in particular offers us, or should I say Meta, offers FISE as an open source framework to conduct semantic similarity search. And some of these systems also and algorithms competed, and they continue to compete. So you might know ANN benchmarks, and also we have big ANN benchmark. So you can take a look at how they compare and how they are implemented. It's also quite rewarding to read these papers. So just to a little bit scare you, this is a huge collection of algorithms. And this is like families of algorithms, based on product quantization or HNSW, inverted index, GPU-friendly algorithms, and so on. We've also invented an algorithm at New IPS, a big NN competition challenge. And this team, which I formed really quickly more than a year ago with Max Irvin and a few folks from Silo AI, my previous company, and also Alex Klivitz. And well, if you're interested in what we did, you can read a blog post, which I linked here. But just to give you a high-level understanding of what we did is that we compared our algorithm with FIS, and on one of the data sets, what you do is that you benchmark recall versus QPS, which is queries per second. So if I said, I don't care about recall, you could be as fast as possible. So for example, recall could be 0, but the other extreme is like recall, absolute recall, and that could be super slow, maybe not achievable at 1 billion scale. So we competed on data sets comprising 1 billion vectors of different dimensionality, you know, from 128 to 256 and so on. And on one of the data sets, we have beaten FIS by 12% in recall, but we didn't do that on billion scale. We could only do this on 10 million, which is still fairly large amount of vectors for practical use cases. And essentially how product quantization works is that this is a slide from Pinecone presentation. So if you have like a vector X as input of dimensionality D, so dimensionality could be here, let's say 512. What you do is that you divide this vector into sort of like shards, vector shards called subvectors. And each of these subvectors will have dimensionality D over M, and M equals 4 in this case. And essentially you kind of like reduce the dimensionality of your space, and now you can operate on a lower dimensionality, which is faster, cheaper to store, but you may end up in a situation that very similar points in your geometric space might be projected into the same point in the new space. So you will lose in recall, but you will gain in queries per second. So we've done also some analysis. In this case, we have used Kolmogorov-Smirnov test, and also we computed variance inflation factor. You will find all the details in the podcast, in the blog post. But we found that these interesting patterns that you see on the screen, I keep jumping, that you see on the screen, there is some regularity in how dimensions of vectors correlate with each other. So they are not independent variables. And these led us to think that we can actually reshuffle the dimensions in each vector in such a way that they correlate much better. And that allowed us to gain 20% in recall. Okay, so why do we care about vector search in general? I did show you the example of text like matching versus semantic matching. Just to give you a bit more, if your data is something else, right? If your data is images, audio, video, what have you, maybe tables, maybe 3D mesh, you cannot really use inverted index anymore. And so you also can unlock new use cases, right? So if you have a bunch of images sitting on your hard drives, but they don't have metadata like textual captions, you can actually use models like Clip, for example, to unlock these semantics for your users. And if we come back to how inverted index works, is that, well, essentially you have a very sparse vector where you have just a few ones and majority of zeros. This is so-called back of words representation. One of the problems is that it doesn't take into account like semantic context, right? Well, it kind of tries to model it, but sometimes it kind of fails. So for instance, if I have a word capital, is it the main city or is it somehow related to some financial term? And also the word order. So if I say visa from Finland to Canada or visa from Canada to Finland, I do care about which results I'm going to see on the screen. Unfortunately, with inverted index, it's not so easy to model. Of course, you can do phrase queries, but then you'll have to do this probably for every query, and that's not very easy to do. But also, if you look at the search engine comparison and search engine track is a sort of a famous challenge competition where different search engines compete for better precision or better NDCG and so on. In the past, let's say, probably like 10 years or more, there haven't been much advancement in how search engines like perform. Yeah, there've been few kind of jumps and so on, but not like drastic changes. But in the recent development, when pre-trained transformers have been introduced into the mix, we started to see these green dots sufficiently jumping in quality metrics above the average systems previously. And this sparked like interest in this, and I think it will continue for years. All right, so vector search in a nutshell. As I said, it's a way to represent your objects, documents, songs, images in geometric space, and usually of high dimension. So it's a dense vector. Unlike the sparse vector, you're gonna have all the positions in the vector filled in with some number. And well, it's just a vector of floating point numbers usually. But it doesn't need to be a floating number, by the way. It could be a binary vector. So here it's a screenshot from Bi-Encoders documentation where it represents it in a kind of three-dimensional space. And you can see that, for example, apple and banana being fruits are close to each other in space, while newspaper, magazine, and article are semantically related terms in another part of the geometric space. So it basically gives you an intuition that that's how semantics is modeled if your model is doing it well. I mentioned that example with the capital, and this is an example from Niels Reimers, one of the former researchers of Hugging Face. So he gives you an example here. What is the capital of the United States? If I use lexical sparse search using, let's say, BM25, it may pull up statements like capital punishment. So it's not the capital of the United States. It just happens to occur with a word with different meaning. It can also find that a capital of Columbus, that Columbus is capital of some state, but it doesn't say, well, in this case, Ohio, but it doesn't say that it's the capital of the whole country. Conversely, if we use neural search, it actually will pull up Washington, DC, so as the capital of the United States. And that kind of drastically changes. And again, it doesn't say, I don't want to say that it works always this way, that vector search will win. In some cases, it will lose. But it does lift your search engine to sufficiently different level. And how you approach, well, re-ranking, if you use BM25, let's say, as your first step, for example, you could. Now in re-ranker, you could use the semantic relatedness between query and a document. And a well-known approach is using Bi-Encoders. So essentially you train a neural network where you encode a query and a document pair, and that's your sample data set, training set. You encode them together in some pooling fashion, and then you come up with cosine similarity that you can then apply during the real-time retrieval. And so this Bi-Encoder approach can overcome the lexical gap. So the issue with building a dictionary in BM25 is that it's a static dictionary, and if you don't have that entry, you will not find what user is looking for. And so you constantly need to play a catch-up game. And this approach will overcome that issue. It also respects the word order. So the example that I gave with the visa from, let's say, from Germany in this case to Canada or vice versa, it will be sensitive to that, and it will return you the most similar answer. Okay. Also, like the use cases that get unlocked with vector search is multimodality that I already mentioned, and also multilinguality. So you could train a single model that can support 50 or 60 or 100 languages, depending on how many input sources you had for training that model. And then you can use that single model to be language agnostic in that language space. So in this case, you know, text embedding and image embedding could also be co-trained in the same model using CLIP, and that gives you multimodality. But if you had a multilinguality, then two dogs in the snow or the same in other languages will find semantically similar items in your database. I wanted to also emphasize the importance of Beer paper. If you haven't read it yet, please do, because as we move forward in vector search, the stability of methods that we use with regards to new domains is going to be super, super important. And so Beer paper actually introduced a collection of different data sets, not only data sets, but also search tasks. So for example, fact checking, you know, question answering, entity retrieval, news, Twitter news, and so on. And all of these have different sort of modes of search, and they've tried all the available algorithms or major algorithms on these data sets, and they show how they compare. And so what's interesting is that the M25 is going to be a very stable baseline. So as you can see, it actually beats quite a lot of algorithms on different data sets across these domains. The only method that is winning is BM25 plus cross-encoder, with an asterisk that cross-encoder is fairly computationally intensive algorithm. And so if you don't have that much of capacity, it might be way too expensive. But the next best is doc2query. And this is a very interesting algorithm, because what it allows you to do is that you don't need to use any vector database. You can stay with your sparse search database like Apache Solr or Elasticsearch. What you do is that you take your document collection, you pass it through the doc2query algorithm, and it will generate you candidates of queries that your users might ask in the future. So it's kind of like an oracle. And what you do is that you will concatenate the document with the query or set of queries, pass it to your search engine for indexing, and now it's going to bring much more similar results than it used to. And you don't need to move to any vector database at this point. You could, but you don't have to. Okay, let's come back to our pyramid. Now we're going level up. So, or 2 levels up, we will focus a little bit on vector databases and neural frameworks. And I'm going to advise you to read this blog post, which has gotten attention from something like 25,000 readers by now. It's a fairly short blog post, just showing you the main features of each vector database. And you can see also the names of people that I had privilege to speak to while writing it. And what's also interesting is that it has a link to another presentation that I gave half a year ago, and I covered these players in much more detail, but pretty much based on this blog post. Just to summarize all the players, so we have, of course, we have why I call this smaller vector database players. It's not to downplay them, but just to show you that there are also, you know, web scale players like, you know, Google, Microsoft, and so on, and Amazon, and they have their own version of vector database in some form or fashion. Here we deal with, you know, databases that are going to be useful for mid-sized companies, for example, maybe even above. And so you have 71% open source databases like VV8, Quadrant, Vespa, Milvus, and Vault. And we also have 2 players, Pinecone and GSI, which are not open source. At the same time, they're all fairly comparable, and you see demos on the market that you can also try out. And of course, you can always check out their APIs and products. They also slightly differ in which languages they're implemented in, which may be not an issue at all for you unless you go deeper and you want to implement something on, on the level of the database itself. I have interviewed majority of these, and so please resort to the podcast if you want to learn more. For semantic search frameworks, we have lower number of open source players, which is quite interesting. So if you remember the pyramid, as we go closer to the user, we start unlocking some user use cases, which are probably something that everyone cares a lot in business. And so to me, it's not a surprise that we will get less of open source players. It doesn't need to be this way, but I think this is a trend that we observe right now. And so just examples of some examples of neural search frameworks like Haystack, Gina, which you can try already today. They have a bunch of interesting demos. Rasa AI, I think, if it can count as a search semantic layer framework for virtual assistants, it's also open source. There are also some that are not open source, like Muves and Ziri, Hebia. Again, they are unlocking some interesting use cases, but it's still worth checking out. And I've interviewed few of these, maybe half of these in the podcast, so please take a look. One thing worth mentioning is that these different frameworks focus on different sort of challenges or tasks or domains. So DeepSet Haystack, for example, focuses, to my knowledge, entirely on natural language processing. The same applies to Ziri and also Hebia. Hebia even goes further, and they unlock finance. But then others like Muves or Gina focus on multimodality, and so they don't only focus on NLP, but offer you tooling for other domains like computer vision and automatic speech recognition. All right, now we are close to use cases. I hope I'm not running out of time. So this is my take on specific versus broad use cases that I have observed in this past couple of years, both talking to people and also reading up and implementing some of the things myself. So I think very specific use cases, image similarity, again, it's a broad niche that you can apply to multiple, products. But I think at this point, Clip is kind of like a winner. And here I link one demo, which is using KNN search on Clip. And it indexes a lot of images from the web. Then another specific use case is multilingual search. If you know in Solr or Elasticsearch, you will have to bring up another shard, another core or collection and configure it with that language, or maybe you will have to come up with a way to mix languages in the same core. So you'll have to scratch your head quite a bit. In vector search, you could use just one single model, as I mentioned before. Question answering is the third very interesting use case for similarity search. There was at some point TechCrunch VB8 demo available. It's not available right now. Maybe it will be in the future. Also, DeepSet shared a demo just today on tabular data. So you can ask questions to tables in natural language. Recommender systems is, of course, another, well, I could say specific use case. For example, Facebook's newsfeed, or I believe Twitter as well. Another one very interesting that came in one of the episodes of Vector Podcast is Google Talk to Books. I don't know if you guys heard of it. So you could actually ask questions to pieces of books, right? To passages of books. And that's quite interesting if you are trying to remember some book you've read, or maybe you're looking for a new one. Another use case is car image search. And you could say it's image similarity, but what struck me is that it's applied to car image search on classic.com. And that's also a very interesting use case in the mix of use cases. And of course, e-commerce. I see a couple of startups working on this, and they apply multimodal search to find product images using text. And a more broad use case space is metric learning, for example. I think Quadrant is pushing this idea forward quite a bit. And I have one podcast with an engineer from Quadrant explaining what metric learning means. Essentially, in a nutshell, if you have a collection of objects, you don't know which model will work best for it. And so you can essentially fine-tune the model. Maybe you chose already the model that is close enough. You can fine-tune it to represent your objects, similar objects closer to each other without much training data. And that's I think, a fantastic way of moving into semantic search space. Another broad example is, well, semantic similarities. So like ride sharing, it's a concept. It's not just these words that I want to find in my document collection, but I may be interested in related like brands like Uber and maybe some logistics and so on and so forth, which revolves this term. And this might be very interesting for investors, for example. Another use case that came from Pinecone is anomaly detection, which I think is also a very interesting broad use case for vector search. Classification is, of course, very straightforward because, for example, if you have a product collection and you have a product taxonomy, you may need to link an incoming product to that taxonomy. And so I've seen real examples of where vector search is used for this use case. And then multi-stage ranking. It's essentially a way to keep re-ranking your documents such that they answer the user question the best. And so if you're interested in this, I recommend you to look for the episode with Vespa Jobergum, who explains this. All right, now the demo time. And this is where I hope some of you can share examples of queries that we can try. So the Talk to Books project that I mentioned here, well, allows you to talk to books essentially. And so, for example, if I check, I don't know, how stop thinking and fall asleep. So you may, well, read a psalm, or like maybe you can memorize it and try to repeat it, or read some philosophers' work and fall asleep guaranteed, says this book, right? So, so this is an interesting way, and this is using distilled BERT model, and essentially it's a neural search, similarity search in action. Another example that I came through just today on LinkedIn is from DeepSet. So what I just mentioned is question answering on structured data. So you can actually ask questions to tables that you can either find in your documents or on the web, and then apply a method of table extraction. You can start asking questions, not as a SQL, but more like a natural language. So I could say, who is the fastest runner, right? And so the system will pull it up from the structured data that it has analyzed. I'm also curious if the audience has more use cases, maybe real world examples of systems that you can share. Please do that in the chat. This demo, and I welcome example queries from you. So here, what it does is that it's a multilingual search, and I'm running this on my laptop right here in a Docker image. And I'm using FICE, and I'm using a model called Distill based multilingual cased V2 model from Hugging Face. And this has indexed 1 million books from Amazon. So it's not the whole collection of books, but some interesting queries like, in this case, this is a query in Finnish, which says how to live a happy life. It's able, without doing any machine translation, to find books on the topic, which is fairly interesting. I can also do that. A lot of language, like something about nutrition and health. Oh yeah, there is one use case from Eden about deduping massive data sets. I think that that's an excellent example. If you want to do some kind of clustering of data, I think this is the way to go. And of course, KNN was used there before, but at scale, you might need ANN. That's an excellent example. Yeah, I can also try my query in Chinese. In this case, it's bicycle repair manual. And so it pulls up a few books. So I think it's fairly impressive that you can run this on a laptop. You know, it's a FICE model, so it's not a vector database. So it does have some limitations. For example, it doesn't support filters, but it does its job. If there are any examples of the queries, let me know. Andre is mentioning finding errors in data sets with similarity search as one use case. I'm interested to hear more detail on that. Sounds really interesting. How does the model handle typos? That's a great example. That's a great question. Let's try it. If I type, instead of this umlaut, I will type just A. It still finds it. Maybe if I do some other damage to the query, it still finds it. So I think it depends on the model, and there are approaches. One model from Google that goes byte level, and so that will be resilient to typos. But to some extent, this also depends on the data that you had used, and so yeah, some kind of string similarity. But that's also an excellent question from Ahmad. Yeah, Lucian is asking, how about when the index is composed of multilingual documents in multiple languages? That's a great example, great question, because yeah, in that case, you will find the documents in these different languages. And so if you didn't want that, if you wanted to find only in specific language, then you would have to apply hard filter. And also if you wanted to find all of these languages, but represent them in the user's language, you would probably need to do machine translation. Okay, let's try another demo for a change. This is a multilingual and multimodal search engine using OpenSearch and using GSI APU. APU is Associative Processing Unit. So it's kind of a card which you can plug into your server, and it will turn your server into a vector database at scale. Yeah, so essentially what we have implemented here, we have image embeddings using Clip, we have text embeddings using universal language transformer, I guess, and then the keyword search is an untuned sparse search in OpenSearch. If you have any examples of queries you want to try, we can do that. I will resort to a list of queries that I have pre-prepared. So in this case, well, the result that you see is red dress. Just to show you that this works, we can try yellow dress. Yeah, so it brings a collection of yellow dresses, and these images were taken from the web, and the data set is called LAN. So it has 400 million images, and for practical purposes, we have indexed 10 million of them. All right, and if I try a query in Finnish, because I'm in Finland, this is a query which is red dress, and I'm going to try keyword search first. Let's see what it brings me. Oops, no, none of these are dresses, as you can see. And the reason for this is because it turns out that some of the captions on the images do contain the word punainen, which is red in Finnish, but they don't contain the other word, which is mekko, dress. It's not here. And because it probably applies some sort of disjunction query, it just happens to find these objects. If I switch to text embedding, multilingual model, that should do better. In this case, it finds essentially now it encodes each of these captions as a vector, and it's doing much better job, as you can see. But maybe not perfect because, well, in this case, it's probably addressed, but it also seems to be matching on the words. So it's doing some sort of optical character recognition. But if I switch to embeddings, image embeddings, here I get, I believe, better results, or like more semantically similar results than with, let's say, keyword search for sure. If I was using this system as kind of retail search engine and I tried canned tomato, with image embeddings, I can find all these interesting pictures of canned tomato of different sort. And so the same probably will apply to text embeddings. Yeah. And then keyword search will still find some interesting ones because we just happen to have that in the textual collection in the data set. There are other examples here. So for example, in Hebrew, if you happen to speak it, this is a red dress in Hebrew, just to show you that multilinguality works. And also, if I try a query in Russian, this is blue shoes. It does bring me some blue shoes. Some of these images don't load because we pull them from the web, so they are not available, they're not loading, but they load sometimes. Yeah. Yes, I think this is roughly what I had. Does anyone have a query they want to try? Lemon dress. Oh, that's an interesting example. Let's see. And we will go with image embeddings. Yeah. Do you like it? Lemon dress. We also had.
I do.
Awesome. We also had like long dress. I think it was sleeveless dress on one of the presentations on Berlin Buzzwords. So here you do get long dresses, but they might not be sleeveless, or vice versa. They might be sleeveless but not long sometimes. And my hypothesis is that models like Clip, again, it might depend on the data that was available during training, but models like Clip, they don't model these properties of an object well. So I cannot just say, yeah, please focus on the color, but also on the shape and also on the size and so on and so forth. And so at that point, I believe you need to resort to hard filters, which is another interesting topic. Who is James Webb? Is this a question, Lucian, is this a question on this search or on book search? Maybe I will try it in book search. I don't know if we will have it, by the way, so apologies if we don't. Yeah, we pull up some books with James, so no web, but yeah, it's just 1 million books. So yeah, there was another one from Andre, colorless, green ideas, sleep furiously. Yeah, I think this is a way to kind of try to break the search engine. Yeah. Again, let me try it with books. The green phantasm, going green without going broke. Yeah, you might like these books, Andre. Check them out. All right. Yeah, Connor is offering another set of queries like long dress. So let's see if that works. Yeah, I think all of these are long. Awesome. And if we go with sleeveless, again, let's see if we will get anything working on this front. Oops, let me copy it. Yeah, you do get sleeveless dresses. Not all of them, as you can see. Number 3 is probably not but the first one is, the second one is, the fourth one is, the fifth one, fourth and fifth, they're all, well, they're all sleeveless, right? So yeah, in that sense, maybe you could do a series of queries, then somehow combine them. I don't know, that's an open question. Awesome, thanks, Connor. Let's come back to the slides. I'm going to conclude really shortly here. Again, the multimodal search demo you saw, these are the sort of high-level technical details, multilingual clip, multilingual sentence transformers, and Leon 400 million data set that is openly available, and even the vectors are pre-computed. So just to conclude where the things are going from my perspective, first of all, a very interesting direction is how you're going to combine BM25 and vector search. There is an excellent talk from the Vespa team. I believe the presenter's name is Lester. He actually showed not only the ways to combine, but also what will be in the result in terms of the NDCG or precision of your search. Gina also has demos with text image blending. So you can see the effect of kind of offering more weight to text, less to image, or vice versa. And you may think about it in your user interfaces as well. If you're not certain what user is looking for, you may offer some ways for them to control the search experience. Another big topic for me, and I think it's going to be big for every user of vector search, is efficient embeddings. So the issue is that if you need to use GPU to go and deploy your neural search at scale, so let's say compute, I don't know, 100 million vectors by certain deadline, you might incur quite high cost. And so Mighty is an example of embedding server which goes quite economical and moves all of these from GPU to CPU with the same latency. And go check out Max's blog posts on latency at scale. Also going multimodal, what I just showed you with Muves, multimodality, hardware acceleration, but even just the new use cases like searching inside audio, or blending it with text-based matching. Again, this will depend on your product. This will depend on the project that you're working on. But I think this is going to be very big in the future, in the coming future. And also things like finding complex objects like 3D mesh. I think Gina has that example. Polygon similarity might be interesting for map search or some of the map maintenance or sort of operations. Another very big topic is model fine-tuning. I know that Niels Reimers is going to give a presentation about this quite soon. I think, again, read the Beer paper. It's, I think, 2 years old by now, but it offers a lot of wisdom how your models are sort of, how they stack up against different domains. Also play with Gina Fine-Tuner. It's all open source and you can try it on your data set and see how well it works. But also try pre-trained models. Like for example, the multimodal and multilingual model demo that I just showed is just using clip. We didn't fine-tune it. We just took images from the web and it works fairly well, maybe sometimes extremely well. Also, when it will fail, we will probably need to fine-tune it. And also, just think more broadly, you need to choose strategy for your vector search. So let's say, if you stay with Elasticsearch, OpenSearch, Solr, or similar system, do you just add a dense vector to your schema and your map or your mapping, and off you go, you have a neural search experience? Or do you need to move to an entirely new vector database? And then do you do what? Do you need to combine them in some way, or you serve different use cases altogether? Also check out Doc2Query. I think it's an excellent way to, dive into vector search without any vector search database involved. You might still need some embedding layer though, but that's solvable. Also, precise versus explorative search. In some sense, vector search offers kind of capabilities of explorative search, so it's kind of recall oriented. But I think it can also offer interesting similarities and semantic precision there. And unlocking these new use cases like multimodality is an excellent way to apply vector search. Then you will need to also figure out MLOps, machine learning operations. I think Gina offers some way to do it with microservice architecture. I think also Viviate has some interesting components there. But in the whole overall system, how you orchestrate this and how you scale this and how you keep it on budget, this is going to be a very interesting topic for MLOps. If you want to get practical, check out this repository. I think it has more than 100 stars by now. It was just a kind of guinea pig for me just to try this in the systems I knew by then, like Solr and Elasticsearch and OpenSearch. But this is extendable, so you can add new systems, new search engines, you can add new models, theoretically any, and go try it out. Yeah, you can follow me at Twitter, subscribe to Vector Podcast or Spotify or Apple Podcasts, and will welcome you as a listener. Thank you very much.